Hi everyone. In this video, I would like to look at question 7 from WACE 2012. I was asked to do this one recently on sector. The purpose of this video is to give you a walkthrough of what I'm thinking while I try to tackle the question. Now you can pause the video here and read the question yourself. But what we've basically got is an electron passing between two parallel plates. There is an electric field between the parallel plates that accelerates the electron. This uniform electric field transforms the electron's kinetic energy from its initial value as it enters the plates to 4 times its initial value as it leaves the plates. We are being asked what would happen to the kinetic energy if the electric field was doubled. Previously in our energy studies, we've learnt that energy is the ability to do work. We've defined work as the change that is being done in the world around us. Work consumes energy. Looking at this question, there is work being done on the electron by the electric field. The transformation in the kinetic energy of the electron is the work done by the electric field. Expanding upon that, when we see that the kinetic energy as the electron leaves the field is 4 times its initial value, then we can say that the change in kinetic energy is 4 EKI subtract the initial kinetic energy. This tells us that the change in kinetic energy is 3 times the initial kinetic energy. Now, before we continue on with the question, we should consider what we have in our toolbox. Our formula and data sheet is our toolbox. We know that work equals force times distance. We think of this as the work equation. In our formula and data sheet, we have the electric field strength equation. And we have to be very careful here to remember that the capital E in this equation is electric field, not energy. Rearranging the electric field strength equation, we have an expression for force in terms of electric field and charge. Capital E is electric field. So, since we know that work equals force times distance, and since we know that force equals electric field multiplied by charge, we can say that the work done on the electron is equal to EQS, electric field multiplied by the charge of the electron multiplied by the distance between the plates. Some people rewrite this as work equals QED, charge of the electron multiplied by electric field strength multiplied by distance between the plates. So, back to the question. In the setup of the question, work is done on the charged particle. The kinetic energy is quadrupled. And so this tells us that work 1, the setup work, the beginning, is equal to QED with the original electric field, which we will call E1. The change in kinetic energy, 1, in that original setup, is Q, E the field 1, D. And the work done on the electron is 3 EKI, or 3 times the initial kinetic energy of the electron. We are then asked what happens to the kinetic energy of this particle if we double the electric field. So we're going to call this situation work 2. We've doubled the electric field. So in work equals QED, the electric field value I'm using is 2E1, which is twice the original electric field. So work 2 equals Q 2 times E1 multiplied by the distance between the plates. Work 2 equals 2 times QE1D. QE1D was what we originally said was work 1. So this tells us that work 2, the second situation, is equal to double the work 1, the first situation. Work 2 is double the original change in kinetic energy. The original change in kinetic energy was 3 times the initial kinetic energy. So work 2 is equal to 2 times 3 of the kinetic energy initial. Work 2 is 6 kinetic energy initial. So the change in kinetic energy, the work, is 6 times the initial kinetic energy. Now, the final part of the question. What is the final kinetic energy as the electron leaves the second plate in this second scenario? Well, the change in kinetic energy, it changed by 6 multiples of the initial kinetic energy. So that's the change. The change is 6. So the final kinetic energy, subtract the initial kinetic energy, equals 6. Now we find out what the final kinetic energy is. Rearranging the equation, we get the final kinetic energy is 6 multiples of the initial kinetic energy plus 1 multiple of the original kinetic energy. The final kinetic energy is 7 multiples of the initial kinetic energy, and that is an answer to the question. I hope this was helpful.